Then why batch normalization is good for generalization? So what is batch normalization? Batch normalization is a very key component of deep structured neural network. Usually when your structure has many layers, batch normalization is very important. Without batch normalization, usually the network performance pretty bad. Okay, batch normalization usually receive many input. Each neuron of batch normalization layer receive many input, and it consists of two steps. At the first, it approximate mu hat and sigma hat, and then normalize the input sequence so that x minus mu hat over sigma hat, which means you make the input signal having zero mean and univariance. Okay, so basically the batch normalization, the first step of batch normalization is purely normalization step. So you take the many input values and estimate the mean and variance, and then normalize the input signal so that the input flow becomes zero mean and univariance random signal. So this normalization idea was very popular idea for simple machine learning tasks as well. So for instance, if you train your linear regression, usually you have to do some step to normalize your input predictor, make each input variable having mean zero and univariance, because this can make your parameters becomes very generalized, and using some other additional technique, you can reduce the generalization gap. Anyway, so the normalization is very important for many machine learning tasks. So from that concept, machine learning researchers invent batch normalization layer, and it turns out batch normalization layer is very powerful to train deep structured neural network. Okay, but the problem is we usually employ stochastic gradient descent rule using mini batch. We do not take the gradient for full batch, full data set, but we randomly sample very tiny portion of your input data to compute gradient, to compute one forward pass inference and take compute the loss value and take the backward pass to compute the gradient. And in ideal case, batch normalization has to have the mean of your entire data set and the variance of your entire data set. So the input sequence or input signal for your entire data set becomes zero mean and univariance. But because we have to use one mini batch for computing gradient, and after gradient you will have different parameters. Actually, taking full data to compute mu hat sigma hat is not good idea and actually impractical. This is not allowed in practice. You have to use mean and variance from the mini batch to implement batch layer. Okay, so because you estimate mu and sigma hat from mini batch, this value is far from what you really want to know. What you really want to know is the real mean and real variance for your entire data set. Okay, so the random selection for constructing mini batch introduce some noise, and the noise for estimating mu hat and sigma hat introduce some generalization property, right? When you take another mini batch, the data can be totally different. So mu hat and sigma hat can be totally different. Such oscillation can introduce very nice generalization gap. By the way, for batch normalization process, after scaling your input x and after you compute xz, you rescale with parameter of batch normalization layer, gamma and beta. So you compute y is equal to gamma times x plus beta, and gamma and beta is they store some information. Without gamma and beta, actually the batch normalization actually just prevent learning. Okay, without this parameter, your learning process becomes very slow, very inefficient. But with gamma and beta, you can slowly store some information of your data, and then you can train something. Okay, this is batch normalization, and this estimation process, because you cannot compute the mean and variance of your entire data point, you have to use mini batch mean and variance, and the mini batch mean and variance always have some noise, and the noise is useful for generalization. So always some bad news for optimization or for training, sometimes good news for generalization to minimize your training error. Okay. And again, because this is some noisy process, and noisy process is good for training but not good for inference. So for inference, you do not use you have to do not use the mini batch mean and variance, but you have to use some averaged mean and variance. So you do not take mu hat and sigma hat from the last mini batch, but you take the average of mu hat and sigma hat. So when you check the batch normalization paper, they utilize some weighted average or just a sliding window based average, so that you can take recent parameters and recent input x values, and from the recent x values you take mu hat and sigma hat, and not looking at single mini batch but looking at many different mini batches, and from the variety of data you can reduce the error to estimate mu hat and sigma hat. For inference, noise to estimate mu hat and sigma hat is not good news at all. So for inference, you take some average and then improve some performance. Okay, you take average mu hat and sigma hat. Okay, so all generalization methods using some additional noise. One very important side remark is we have to use the noise only for training, not for inference. For inference, we have to turn off the random noise process. We have to remove the noise to improve the performance. Batch normalization is very important for training deep structured neural network. So because of that reason, there are many variants of batch normalization. So if you are interested in this kind of concept, I want to recommend few names: layer normalization and instant normalization and group normalization. And these techniques use a different sample point or different work to estimate mu hat and sigma hat, and you can easily find out very nice summary paper or summary document from Google, and I strongly recommend to check out such web page and such blog posts and some survey papers, and all these four variants use incoming data point to estimate some mean and variance of some block of your input space, and then using mean and variance you normalize the block structure so that the block structure having zero mean and unit variance. Batch normalization take average and take the variance computation from mini batch for one single channel. So you take the entire image map for one given channel using many different data points in one mini batch. Layer normalization, they just use one single data point, but it uses whole channel space. So for one single data point, it takes the average for one entire layer and compute the variance for one entire layer, and then make the entire layer containing zero mean and unit variance. Instant norm look at some different area, and group normalization look at some different area, and each paper claim such normalization, new normalization technique improve the performance for some specific applications. And weight normalization, this is something different. Instead of normalizing incoming data signal, weight normalization, which normalize the weight. So weight normalization make the weight of each layer having zero mean, sometimes unit variance as well. Okay, so all this normalization technique, only different thing is where we have to normalize, which layer we want to normalize, which portion we want to normalize, which part we want to normalize, and so on. And each normalization technique has pros and cons, and each normalization technique always makes some noise for training process, and each normalization technique always makes less noise for inference task. So they leverage some averaging technique. Okay. And another interesting side remark is SGD was optimization technique, and it has some noise because it takes a gradient with mini batch, and the noise can improve the generalization performance, right? So for this kind of loss control, SGD oscillate around the true optimal point because of constant step size and noise, so which prevent your model to fit it to your data point, but your model can have more general decision. So this is good for your training, but for inference, as in dropout and batch normalization technique cases, for inference cases, such noise might be not useful. So again, we can take some kind of average for inference task. So this paper is about that, averaging weight lead to wider optimal and better generalization. So the main idea of this paper is when you have this kind of trajectory of your SGD, do not take the last time parameter, but take the average of your trajectory, some last few trajectory point, and take the average. Then, as before, maybe we can remove some noise, and maybe we can do better for inference. Okay, so this is also very interesting and very practical trick. And it turns out that this very simple technique really helpful for many applications. So maybe you can try it as well. Okay.